In today's lecture, we will consider problems of impact and collision. That means we will consider, let us say we have a body 1 which is moving with some speed, say v1I, and we have a body 2 which is moving with a speed of v2I. These bodies are moving towards each other and then they touch each other. This is body 1, this is body 2. They touch each other and this is what we call as impact, and after impact the bodies separate again. So, this position we have called as I, and the position just after impact we will use the subscript F. So, what we have is two bodies 1 and 2 of mass m1 and m2. They impact each other and move after the impact, and this impact can also be called as a collision between two bodies. So, what we will understand in today's class is the mechanics of this impact. If we know the bodies are approaching each other, the one body has a velocity v1I, the other has a velocity v2I, can we find the final velocities of these bodies using the laws of mechanics? So, that is what we will see, and what we will realize here is that the impulse momentum principle is the one which we will use to solve these problems. So, this impact, one thing which we will realize, if we let us try to characterize impact, this impact takes place over a very small period of time. And the impact forces which cause the collision, they are large. So, therefore, impact can be treated as an instantaneous impulsive force, and the analysis which we are going to do will be the analysis of the body just before impact, that is I is the position which we will refer to for just before impact or pre-impact, and we will use the subscript F for the position which we have, or the configuration actually I should be saying, just after impact. And because the time of impact is very small, what we will assume is the position of the bodies do not change. That means, during this impact time, when a body is coming hitting the other one, we are analyzing this position just at the time of impact. So, the position of these two bodies will not change. So, now let us define some of the parameters and let us look at this analysis. We are drawing body 1 and body 2 at their time of collision. So, clearly what we can define is T is the tangent plane of the bodies. So, when the bodies are touching each other. So, the tangent to these two bodies is what we refer to as T, and in two dimensional, when we do 2D analysis, this T will be a line. If it is 3D analysis, then T will be a plane, but in two dimensional analysis we look at the two bodies which are touching each other and we draw a tangent to these bodies, and this is what we call as the T direction. And this, I think, should be very straightforward for each of you to get. The next thing what we do is perpendicular to T. So, we have figured out what is the T direction. Perpendicular to T in this plane is what we call as the N direction, and we will call this as the line of impact. So, these two things are very crucial. Finding the tangent plane and perpendicular to this tangent plane is the normal plane. So, if this is what we have called as T, we draw a perpendicular to T on this, and that is what we call this perpendicular to T is termed as the line of impact, and we use the symbol N for this, and we will realize that this is very crucial to solving the problems. So, that means when we have two impacting bodies, we identify T, the what we call the tangent plane, or we can call it as the plane of contact, and N, the line of impact. Now, let us try to analyze some of these things. The impacts we will be talking of will all be referred to as smooth impact, and what we mean by smooth impact is that the impact force on each body separately is along the line of impact. It can have any direction along this line, either plus or minus, but in a smooth impact the impact force is along. So, that means if we have this body touching this body, this is the tangent plane, this is the line of impact. So, the collision force is only along the line of impact. So, that means if I look at this body, if it is a smooth impact, then the force of collision on body 1 is along this direction, and force of body 2 at this point of contact is along the N direction. So, force of collision is along N. So, collision force only along N for smooth impact. Why do we call it smooth impact? Because there is no force in the tangent plane, and the tangent plane is where the friction would come. So, therefore, because the impact or the impulsive force is only along the line of impact and there is no force along the tangent plane, we call these impacts as smooth impact. And the impacts which we will be talking of will be only smooth impacts in this course. So, as we have said, we have already written what is I and F. I will denote the pre-impact configuration, F will denote all quantities which are post-impact. Now, we define one more term. We define a collision as a direct or a head-on collision if V1I and V2I. V1I is the velocity of body 1 before impact, and V2I is the velocity of body 2 before impact. So, direct or a head on collision is one where V1I, if V1I and V2I, if these vectors are only along n direction, then the collision is said to be a head on or a direct collision. So, how do we decide? If a collision is head on or direct? And the simple way to do this is draw the tangent plane or determine the t direction, and also once you draw t, you will get the n direction which is perpendicular to t, and then see V1I and V2I if either of V1I or V2I has a component along t which is not 0, then the impact is not direct or not head on, and we call such impacts as oblique impacts. So, that means we have decided this, and what so we have now talked about impact of two bodies, and we have also decided, we have talked of what is a direct collision or a head on collision. So, that means each collision problem which you come across, it will either be a case of direct collision or an oblique collision. Now, let us see in a typical problem. Normally in a problem, the initial velocity of body 1, initial velocity of body 2, m1 and m2 are given, and then we are given that these bodies impact and they go away after impact, and we wish to find V1F and V2F. So, we have two bodies, they come and impact, the initial conditions are given, we have to find V1F and V2F. So, now what we do is, let us do a simple analysis of these bodies. So, let us mentally draw, let us say we have a body 1 coming like this, and we have a body 2, and such a collision as we have shown here, this is a head on collision. I will look at an example of oblique collision a bit later. So, we have this body now. When the body 1 is impacting body 2, during the collision, what we find is there is a force F, and the impulsive force, this is an impulsive force, and the impulse of this we can write it as integral f dt on body 1. Similarly, when I look at body 2, the impulse on body 2 will be equal to minus integral f dt. Why is this impulse on body 2 minus integral f dt? This is because the action and reaction between body 1 and body 2 are equal and opposite. So, the impulse on body 2 will be equal to minus of I. Now, if we apply impulse momentum principle on body 1 first. So, on body 1 what we have is, this is the impulse which is acting, we show it as I, and initially the momentum is m1 v1I, and finally the momentum is equal to m1 v1f. Then what the impulse momentum principle tells us is, the impulse momentum principle tells us m1 v1I plus the net impulse, we have to take it with the right sign, is equal to m1 v1f, or this can also be written as impulse is equal to the change in momentum. So, this is what happens to body 1. Now, if this impact is a head on collision or a direct collision, then what we know is v1I is only along n. So, what we should do is, we should first show the n direction. N direction is along the horizontal, and if v1I is only along n, what we find is, that means in v1I the tangent component is 0. Now, impulse is also only along n because this is a smooth impact. So, because both of these are only along n, v1f will also be only along n. So, if v1I is only along n, that is, it is a case of a head on collision, that means T component of v1I is equal to 0, and what we find is the impulse is also along n, it may be plus or minus. So, therefore, v1f is also along n, and T component of v1f is equal to 0. So, this is what will happen in a head on collision. Now, what if the collision is oblique? If the collision is oblique, that means we have, this is body 1, this is body 2, and suppose the velocity of body 1 is at an angle. Now, at the time of impact, if we draw the diagram, this is the t direction, this is the n direction, then what we find is, I have changed this to v1I. So, now initial velocity of body 1, if we look at v1I, this has n component and this has a t component. Both these components are not equal to 0, and this will be a case of an oblique impact. And now, if I look at the impulsive force is only along n. So, what can I say about the t component of the momentum of body 1? The t component will not change. Why will it not change? Because impulse on the body 1 is only along n. So, therefore, what will I get is, if I write v1t initial, this will be equal to v1t final. So, the tangential component of the velocity 1 That means this component now, if I draw this, this is V1t, this is V1ni. The tangential component of body 1, whatever is the initial component, just after impact, the velocity's tangential component will stay as same. And this is what we have written in case of a smooth impact. If the impact is oblique, then V1ti is equal to V1tf. Actually, this also holds for a direct collision, but in a head-on or direct collision, V1ti is equal to 0. So, therefore, V1tf is also equal to 0. And the same thing, same arguments hold for body 2. So, for body 2 I will have minus of impulse which acts here, I impulse acted on body 1. So, minus I acts on body 2, and then we have V2I was the initial velocity, V2f is the final velocity. So, again what will happen is, since impulse, this is the n direction, this is the t direction, impulse is only along n, what we get is V2 t initial is equal to V2 t f, and the normal components change. So, now when we write the equations, if we assume it is a direct collision, first let us look at a direct collision. That means our unknowns are, when we solve, we have V1f and V2f, which are along n. Now, there are no t components in a direct collision, and so we have two unknowns V1f and V2f. And if I write equations, so for body 1, what we will have is, this is body 1, this was, it's travelling with V1i, m1 V1i, and then there is an impulsive force like this, minus the impulsive force is equal to m1 V1f. V1i is known, m1 is known, impulse is unknown. In fact, this impulse is also a scalar because it is only along the I direction. So, I should remove the vector sign, assuming that it is only along n, and V1f is also an unknown. So, there are two unknowns. We write this equation now for body 2. In body 2, we have the impulse acting like this. So, we have m2, and body 2, let us say, initially is moving like this. So, now we are taking this as the positive n direction. So, initial momentum of body 2 is minus m2 v2y plus I is equal to m2 v2f. All the unknowns, we will assume them to be along positive direction. Now, notice I have written these equations assuming the right hand n as positive, and that is why I put a minus sign here. Now, if I count these equations, V2f is also an unknown. So, now when you see these equations, then this I has already been counted. We have one unknown I, the second unknown V1f, and V2f is the third unknown. There are only two equations, and so that means we are one equation short. Another way of writing this is, we write the momentum equation in the n direction for both the bodies together. So, we consider a system considering bodies 1 and bodies 2. So, this is the alternate approach. If we put both the bodies together, then what we find is initial momentum. So, we are talking of a case, this is V1i, this is coming with V2i, and these bodies are hitting each other and then they go. We call this as the positive n direction, and V1F and V2F we assume positive along n. If we get anything with a minus sign, that means it is along minus n. So, if we write the initial momentum along n direction for both the bodies put together, this will be equal to m1 v1I minus m2 v2I. This is along n. And for both bodies put together, the impulse for both the bodies as a system is equal to 0, because there is an impulse of I on body 1, impulse of minus I on body 2. When you add these two is equal to 0. So, that means the momentum of both bodies along n direction must be conserved, because there is no impulse. So, what we get is m1 v1I minus m2 v2I is equal to m1 v1f plus m2 v2f. And once again we find this is just one equation and there are two unknowns. So, these are the two unknowns and there is one equation. So, we are one equation short. And typically in these problems when we are one equation short, we need some extra information. So, we need and this extra information comes in the fact that either we will say, and we will generalize this, but most of when you start off doing this, we say, we talk of a collision as either an elastic collision or fully non-elastic collision. And the general expression for this, we can express it, and I am going to do it in that way. We express it in terms of an empirical quantity, and this quantity is termed as coefficient of restitution, and the symbol which we will use for that is E. So, we will talk in terms of a general expression as how things will be in terms of E, but when we talk of an elastic collision, this will mean that the value of E, which I am going to describe now, explain now, will be 1. For a fully non-elastic or a plastic collision, E will be equal to 0, which will mean that both the bodies will move with the same velocity just after collision. That is the case when E is equal to 0. So, let us try to explain this term E, but what you will also find is when we talk of elastic collisions, in an elastic collision which corresponds to E is equal to 1, that is the same thing as saying that kinetic energy of the two bodies together as a system is conserved before and after collision. So, we will see the meaning and the mathematical implications of this, but if a collision is not elastic, then the kinetic energy post collision is less than the kinetic energy of the two bodies pre-collision, and this extra or the lost energy which is there in non-elastic collisions may be converted to sound or internal energy of the two bodies and may show up as heat. So, in a non-elastic collision, kinetic energy is not conserved, and this lost energy could come in these forms. In elastic collision, the kinetic energy is not lost, it is conserved. Now, as we said, the completely inelastic collision is the case we have talked about E. I have talked about E is equal to 1, E is equal to 0 without explaining what E is, which I will do just in a moment. But if it is a completely inelastic collision, that is a case when E is equal to 0, and at this time the V1F and V2F in the n direction. So, we are looking at the n component of V1F and V2F. What are these? V1F is velocity of body 1 post impact, V2F is velocity of body 2 post impact. In the n direction, these are equal. When E is equal to 0, then V1F n component of V1F is equal to n component of V2F. F means we are talking of just after impact, both of these velocity components are equal, and this is the case of E is equal to 0. Now, how do we work out what is E, or coefficient of restitution? And this, as we said, is an empirical quantity. It will be given to you, it depends on the two surfaces between whom the impact is taking place, and the way we write E is equal to, let us understand this very well. This will be minus, let us first write this, relative velocity of separation divided by relative velocity of approach. Let us understand how to do this. Let us very carefully see this. First of all, when we talk of separation and approach, so separation will mean when the bodies are leaving. So, this is separation. Approach is when the bodies are coming together, for the case which I have done. So, separation is always post impact and approach is pre impact. So, that is what we mean by separation and approach. But one more thing we mean in separation and approach, when we talk of separation and approach, we will only talk of the n component of the velocities of the points which are impacting each other. So, we have point A here, point B here. So, when I talk of, I look at VAN, VBN. So, n component, so this is the t direction, this is the n direction, the point of contacts here are VA and VB. So, VAN and VBN, they will give me the separation and approach velocities when I talk of coefficient of restitution. Of course, when we are talking of case of translating bodies, VA is equal to V1 and VB is equal to V2. When we later on talk of rotation, then Va may not be equal to V1 for the whole body, but currently Va is V1, Vb is V2. When we talk of separation, that means I am talking of VAN final, and when I talk of approach, I am talking of VAN initial, and similarly VBN. Now there is one more term which I have written here, relative velocity. Now let us understand this also. When I say relative velocity of separation, let us understand this. So this is point A, this is point B, and this is just after impact, let us say, and what we have said is post impact we have assumed if this is the end direction, everything is positive. So now when I talk of relative velocity of separation, then what I am talking of is Va final n component minus Vb final n component. Let us understand this. Relative velocity always means Va minus Vb or Vb minus Va. So I have taken A as first. Both these velocities are along the positive n direction, that is what we have assumed because we do not know their directions. So relative velocity of separation will be Vaf n minus Vbf n component. Is that clear? Let there be no confusion about this. So it is velocity of the two contact points, their normal components and their final, and because we are talking of relative velocity, that means we take one of them first, the second afterwards, and we put a minus sign. So this is relative velocity of separation. Now for the problem which we have done, let us look at, so that means for the given problem which we had, which means we had mass m1 coming with V1I, mass m2 coming with V2I, this was V1F unknown, this was V2F unknown. So that means now here let us write relative velocity of separation is equal to, we have written V1F minus V2F. Now let us write relative velocity of approach. Now relative velocity of approach will be, because we have taken 1 in the first and 2 second, we will follow the same thing. So we write first V1I, this is the normal component of velocity of 1 and it is in the positive n direction, so we just write it as V1I. Then I put a minus sign because it is a relative velocity, and then for body 2, what is the velocity of approach in the normal direction? It is minus V2I. So I get V1I minus V2I. Is that clear? And when we do this, finally we will write E is equal to minus relative velocity of separation divided by relative velocity of approach. So E will be equal to, now we have a velocity of separation, so first we put minus of V1, so velocity of separation is V1F minus V2F, so minus of V1F minus V2F divided by relative velocity of approach is V1I minus V2I, so this becomes V1I plus V2I, because it is given to us V2I is in the minus n direction and we have already accounted for this. So from here what we get is E multiplied by V1I plus V2I is equal to V2F minus V1F, where both V2F and V1F have been assumed to be positive. So this is what we get for the problem where we started with using the coefficient of restitution. So, once we have this, so let us now write this equation. Our equation was m1 v1 I minus m2 v2 I, this was the initial momentum, is equal to m1 v1 f plus m2 v2 f. This is what we had, and now to that we add the second equation. We add E is equal to v2 f minus v1 f divided by v2 I plus v1 I. So, now this gives us the second relation. Now, we have two equations, equation 1, equation 2, and we have two unknowns, v1 f and v2 f. So, what we can do is we have this relation. So, from here what we can write is v2 f is equal to v1 f plus E times v2 I plus v1 I. This comes from equation number 2, and this we can substitute in 1. If we substitute in 1, so we will get m1 v1 I minus m2 v2 I is equal to m1 v1 f plus m2 times v1 f plus E v2 I plus E v1 I. And now we can work this out. When we work this out, what we will get is, we work out separately, we simplify these expressions, we will get v1 f is equal to m1 v1 I, and then we have minus m2 times v2 I plus E times v2 I plus E times v1 I divided by m1 plus m2, and v2 f is equal to m1 times v1 I plus E times v1 I plus E times v2 I minus m2 v2 I divided by m1 plus m2. You do not need to remember these formulas, you just apply these equations and you can then work out these different type of problems. Now, you will get many simplifications, when you work these problems out, there will be many simplifications. You will have cases, for example, m1 is equal to m2. If m1 is equal to m2, then these will go away. In the denominator, you will just be left with 2. m1 and m2 are equal, so you will get a 2 in the denominator, you will get this. Okay. Then you could talk for a case of elastic collision, you put E is equal to 1. So, if you have an elastic collision, put E is equal to 1. So, this will become 2 times v2 I plus v1 I, this will become 2 v1 I plus v2 I minus m2 v2 I, and so on. And if it is a plastic collision or totally inelastic collision, then you put E is equal to 0. If you put E is equal to 0, you will get m1 v1 I minus m2 v2 I, and this will become m1 v1 I minus m2 v2 I. So, we will get this, and in case actually what happens is, when you have plastic collisions, then you can directly use the momentum equation, because there what you have is your initial equation was m1 v1 I minus m2 v2 I. Now, because both the bodies, so for this case, since post collision both the velocities are equal, so that will be equal to m1 plus m2 times v2 or v1, both are equal f. So, in case of inelastic collision, actually life is, in terms of equation and solutions, much easier. When two bodies merge together, all you do is take the initial momentum with the right signs. We have a minus sign because v2 I was in the opposite direction. If both the bodies were moving in the same direction, then this would have been a plus sign, is equal to m1 plus m2 times v2 f or v1 f, because both of them are equal. So, this directly For the plastic collision or inelastic, totally inelastic collision, you directly get your answers without even having to bother about writing the coefficient of restitution relation. Now, as I told you, what one can show is E is equal to 1 corresponds to half m1 v1 I square plus half m2 v2 I square is equal to half m1 v1 f square plus half m2 v2 f square for the head on collision case which we did just now. And this could be used as the second equation instead of using E is equal to 1. These two equations are identical. Now, you will find one more thing which is there, which is done in many textbooks, and which is a smart way of doing things. What they do is, they talk of this analysis which we have done on the head on collision. This analysis is done assuming V2I is equal to 0. So, that means this could be a case, first of all we have a ball moving with V1I hitting with this and V2I is equal to 0. Clearly for that, this is the case which is being dealt with. But even if V2I is not equal to 0, as the case which we have done, then we can change, we can do a change of reference frames and study the motion in a frame moving with a constant velocity of V2I. So, if we study the motion in a frame which is moving with the velocity of V2I, in this frame V2I is equal to 0 and V1I will become equal to V1I minus V2I. So, that sort of a change you have to make. V1I in the new frame is equal to V1I minus V2I. But the advantage of this will become that V2I becomes 0. Now, the question which you may ask is, will Newton's law hold in this reference frame? The question is very logical, we have to answer this. Will, if Newton's law, because Newton's law are valid only in an inertial frame of reference. And where are we using Newton's law? We are using Newton's law in the impulse momentum relations. So, therefore, if Newton's law is valid, then our equations are valid. Now, the answer to whether Newton's law are valid or not comes from the fact that we are talking of a frame which has a constant velocity. So, this frame is also an inertial frame, therefore, Newton's law will be valid. Now, some simple things which we can see, for example, let us say we are looking at a frame where V2I is equal to 0, and let us look at an oblique elastic collision between two bodies of equal masses. So, this is body 1, M1 and M2 are equal. So, maybe I should draw it better, I should draw them of the same size. So, we have body 1 and body 2 which are hitting. Body 1 has a velocity V1, this is the tangent plane, this is the normal plane, this is an oblique collision because V1t is not equal to 0. Now, if we write, and we are talking of elastic collision of bodies of equal masses, and we are writing it in a frame where initial velocity of V2 is equal to 0. So, if we now write the equation of conservation of energy, what we will get is half m1 v1 square is equal to half m1 or half m1 v1 I, let us write it. So, we put I also, half m1 v1 f square plus half m2 v2 f square. This comes from conservation of energy, which follows because E is equal to 1, and because m1 and m2 are equal, they can be cancelled out, and what we get is v1 I square is equal to v1 f square plus v2 f square. So, for example, in this case this was v1 I, then v1 I square is equal to, so now after the collision, if v1 f and v2 f are the two velocities of the two bodies, that means suppose if ball 1 is going like this, this is v1 f, then what we know is, because actually in fact this would be a wrong way, let me draw it again, because that will definitely not work, because v1 I square is equal to v1 f square plus v2 f square, that means these three form a right angle triangle. So, if this is v1 I and if this is v1 f, then v1 f square and v2 f square, sum of these two is equal to v1 I square. So, this is a right angle triangle, which means that v1 f has to be perpendicular to v2 f. And so, what we can get from here is that the two velocities v1 and v2 will have to be perpendicular to each other post impact. So, if there is an elastic impact, an oblique impact of two bodies of equal masses, then what we have shown by here is that post impact these two velocities v1 f and v2 f have to be perpendicular to each other. So, these sort of conclusions one can draw and one can get here. So, now we have seen the basic principles of law of conservation of impact and collisions. Now, one more thing let us see, and the last thing which I want to show in these equations is that suppose if body m2 is very massive, that means m2 is much bigger than m1. If m2 is much bigger than m1, where would we have a case like this? This case would occur when body 2 is something like the, so that means body 2 could be earth. We talk of throwing a ball on the surface of the earth. Now, here let us look at these equations. We have derived this, v1 f is equal to this, v2 f is equal to this. Now, body 2 is very large. So, what we do is, whenever this is the case, let us, we have this relation, let us show this, is equal to, I will do it for one body, m1 v1 I minus m2 times v2 I plus e v2 I plus e v1 I divided by m1 plus m2. So, now what we do here is we divide RHS numerator and denominator by m2. So, what we get here is this becomes equal to m1 by m2 v1 I minus v2 I plus e v2 I plus e v1 I divided by m1 by m2 plus 1. And because m2 is very large, then this term m1 by m2 will be a very small number, this can be neglected, and what we get is v1 f is equal to minus of v2 I plus e times v2 I plus e times v1 I. And suppose if v2 I is equal to 0, then what we get is V1f is equal to minus of E times V1I. So, if V2I, that means if V2I is equal to 0, which would be the case when a ball is hit on the surface of the earth, then what we get is V1f is equal to minus E times V1I. And similarly, when we look at the equation for V2f, that will become equal to minus of V2I. So, V2f will become equal to minus of V2I, and if this is 0, then of course it does not matter, otherwise V2f becomes equal to minus of V2I. So, this is how one can work these equations. Here again what I have done is taken this, divided everything by m2. So, we can get our relations like this. And in the next class what we are going to do is we will look at some of these problems involving a single particle, where we will be using different methods. Methods we have seen are method of energy conservation, kinetic energy plus potential energy is equal to work done by other forces. We have seen the method of law of conservation of momentum, and how initial momentum plus impulse is equal to final momentum, and combination of these, how do we use them to solve complex problems in single particle mechanics. That is what we will do, and that will bring us to an end to mechanics of a single particle. And what conceptually we will do in the lectures after that, after we do some examples, will be problems of rotation, talking about what is a rigid body and mechanics of a rigid body, which is referred to as rotation and problems of rotation. Thank you.